we're getting a little confused. So if we have a little patient here, let's make him a bigger patient. All right, so we've got this patient on our table, right? And they're laying there, and we take our transducer, and we want to image the liver, which is kind of in this range right here, okay? And so we send out a pulse. Probably should use a different color for our pulse. We'll use black. And our pulse travels for, say, 30 centimeters, okay, and then returns. The echoes all come back, right? But your question, I think if I understand you correctly, is that pulse actually keeps going and is still sending out echoes, right?
Yes and
What happens to it?
So the pulse goes out, so it hits the top of the liver, and
Yeah.
then the echo comes back from that top of that liver.
Right.
But then after that another pulse comes out, right? But,
Right.
So that initial pulse is the same one that hits the bottom of the liver and sends that echo back.
So let's
it
say
kinda
we're,
interferes with
yeah,
each
so
other.
let's say we're just imaging to this depth here, okay? What happens after that pulse, all the echoes come back from that depth? We want to send out another pulse, and I think your question is, well, what about the echoes that continue from the first pulse?
Yeah, like in the
Right.
same line.
Yeah.
I'm talking about everything in
Right.
that same line with that one
Yeah.
structure, with that one
So-
crystal, ignoring the rest of them. Just
Okay.
that one section.
Single purpose. If we create a pulse repetition period, and this will be our period, our PRP that we need to do, let's say 7 centimeters, right? Okay, so it's going to be about 91 microseconds long, right? That's our minimum PRP before we can send out another pulse. But you're saying the pulse keeps going, and at 8, 9, 10 centimeters, it's still sending echoes back, right?
Yeah, well, and two, like,
Well-
so it gets that first echo.
Yeah.
But then.
So here's how the manufacturers deal with that, and this is straightforward. They create a PRP that is actually 10, 20 times longer than they need. All right, but they only listen for the first.
How does it know that it's that first pulse and not the echo from the next structure in that line?
They wait till it dissipates. Remember, as the pulse keeps going, it eventually all becomes absorbed as heat. And they just wait long enough for it to be absorbed.
So it just keeps recording the echoes for that line even after it sends out more pulses? Or
No,
does
it just stops recording. It says, we only wanted to listen for 91 microseconds, because we only wanted to hear what the echoes were from 7 centimeters deep. So we're not even going to listen after that. There are echoes coming back. We don't care. We're just not going to listen for them. And so it stops the picture whatever depth you tell it to. Okay? And remember, that's for today. Okay? When we go deeper into these systems, after you have enough vocabulary, I'm going to teach you how they do it in reality so that they can send out multiple pulses. Okay? Do you need to know that today? No. Just assume that they make the time between the pulses long enough for all the echoes to dissipate, and then they send out another one. Okay? But they only listen to the depth that you tell them to. Okay? If I want 10 centimeters depth, I'm going to listen for 130 microseconds. Okay? If I want to go 20 centimeters deep, I need to listen for 260 microseconds. but I'm probably gonna not send out another pulse till maybe 400 microseconds. That's one way to do it. That's how this one does it. That's how any of your older machines do it. Anything made from 1990 does it differently.
What is this machine?
Looked it up today. This was actually manufactured in 1986. I thought it was about a 1982 machine. It's a lot newer than I thought. Fragile, do not drop or hit. Zerreklich. Bitte nicht stoßen oder rufen. Made in Germany. Did I pronounce that even close?
I thought it was Dutch, but it was close.
Oh, okay, well, maybe that's me, I don't know.
No, but to me, Dutch sounds kind of German, but not quite.
Well, whatever.
I understand some words.
All right,
You try.
I went to Germany and,
Oktoberfest.
well, yes, if you must know. But I was with my mother because she was living there in Munich, and she asked, and so we went out for a walk, and the first people I ran into, I'd been practicing German for months before I got there, and I said, Guten Morgen,
Oh my God.
And-
No, that's really good.
and my mother looked at me and said, don't say that here. I'm like, what? Well, it turns out we were in Bavaria where they have a different language. They speak Bayerisch, and so you would say Gusko if you greet somebody on the street. And I'm like, well, that wasn't in the book. I don't know.
No, dialects can, my mom was from the north, my dad's south, they couldn't always understand each other.
Probably made for a better marriage. So the pulse repetition period is our time between pulses, and the theoretical thing is that this is what adjusts for the depth, okay? Now, we just discussed that, a shallow pulse is going to continue on sending back echoes from a deeper structure, but for us today, and really forever, the PRP is our depth, okay? And so the PRP is directly related to maximum imaging depth. And I should say the minimum PRP, okay? Because you can have a longer PRP than you need, you just only listen for a certain period of time, and that's what I was trying to explain.
I have a question on that.
Yeah, go ahead.
So on this slide, it has deeper imaging with a longer PRP.
Correct.
But there's also gonna be a longer listening time.
Right?
Yeah, okay, just wanted to make sure of that.
Yeah. Yeah, because, again, the P part, the pulse part, doesn't really change. The pulse is still the pulse duration, whether you're imaging 10 centimeters deep or 30 centimeters deep. The pulse duration doesn't change. It's just the number of cycles times the period. And so that all depends just on your frequency that you have. And those of you that had lab this week already hate me for that one. So the PRP is the maximum imaging depth you can have with that amount of rest period in there. Okay? Did that answer your question?
Yeah.
Okay, so we got all the questions answered. Good. Okay. PRF is the sound energy pulsed into the body that varies with image depth. It's the frequency. It's how many times I can make those pulses in 1 second. PRF. It's just simply the reciprocal of the PRP. as you get more and more experienced with ultrasound, you will not refer to the PRP very often. Okay, we almost always talk about the PRF. We use the PRF all the time. Old sonographers will come up behind you and say, adjust your PRF. They won't say change your PRP or adjust, well, they will tell you to change your depth. But we use the PRF for other things. Okay, remember, the pulse is our only tool, and we're going to find lots of ways of using that pulse. And so adjusting the PRF has a lot of importance in other parts of ultrasound. Okay? So everyone know what PRF is now. I do want to say one little thing about the PRF, and this would have been a nice one to say before the test, I'm sure. But the PRF is always, the frequency of the PRF, the pulse repetition frequency, is always going to be somewhere in the audible range. Okay? Yeah. So our ultrasound frequencies are always in the, by definition, ultrasonic range, right? PRFs are always in the audible range. Once in a while you'll get a patient that goes, oh, I can hear that frequency. It's like, what they're hearing is the frequency of the multiple pulses creating the PRF. It's in the audible range. I believe they can hear it. Okay.
Your machines in there are loud.
Yeah, that's probably why I'm deaf.
You can hear like so much, like
You mean in-
piercing.
Yeah,
In
and
our
when you
lab?
change your depth, it goes,
Yeah, they
you
go.
can change, you can hear the frequency.
And it's just
that way.
Okay, so that is the PRF you're hearing. If you're changing your depth and you're hearing
Yeah.
a change in frequency coming from the probe, that's the PRF. And it's in the audible range. So if you would have known that on the test, you could have picked that question where it had the, what is the range of the PRF, and it had 4 kilohertz to 15 kilohertz. Boy, that'd have been a dead giveaway. Well, don't forget it, because you might see that again on the next test. 4 kilohertz. Anything audible is within the range of the PRF. So don't write down 4 to 15. That was just that one question. You can write it down. It was. I don't care if you write down that question. You already had the question. Ain't gonna do you no good now.
So PRF doesn't affect that?
Yes, PRF absolutely affects depth. Yes. I don't want to confuse you on that. It's the reciprocal of the PRP. If you increase your PRF, you're decreasing your depth.
So frame rate and frame period are reciprocal.
Yeah. All frequencies and periods are reciprocals. Just go with that.
You said increase.
Pulse repetition period, pulse repetition frequency are reciprocals. I said what?
You said PRF increase is decrease in depth.
Yeah, yeah. Because it decreases the PRP. And we already went over PRP. Yeah.
I'm confused how you said you can hear the PRF,
Yeah.
but you can't hear like just the pulse frequency of it? Like it's an ultrasound range. But
So I want you to work with Nicole on that. She's going to show you how you can change your depth and how you'll hear that change.
The one in this corner is like super loud.
yeah, I know that, but
Yeah.
Yeah. It's, some people can hear it. I couldn't hear it. I'm too deaf. I'm too old.
I couldn't
I
hear it.
can't hear it.
I can.
Pay attention next time you're scanning and you'll hear it.
Okay.
You will.
But more importantly, PRF is depth. Okay? PRF is depth. If I turn down my PRF, I can image deeper. Right? Right. PRF is the opposite of PRP. So if I turn it down,
Because you're making the listening time longer.
yeah, that's it. Right, I can't pulse as many times in a second if my listening time is longer, so my PRF has gone down. That's absolutely right. PRF, just simply the number of pulses in 1 second. All right. So imaging depth and PRF. When the depth is shallow, the PRF is high. When the depth is deep, PRF is low. And the book gives you this way of calculating the PRF in hertz of 77,000 centimeters per second divided by the imaging depth in centimeters. That's lovely. Personally, I don't do that. If I ever have to calculate my PRF, I take the fact that the PRP is 13 microseconds per centimeter. I calculate my time to make one line, one scan line, using the PRP, and then I just take the reciprocal. That's how I do it. I don't like memorizing 77,000 centimeters per second. But if it helps you, there it is.
So you do what's on the right.
Yeah.
So you're not gonna make us memorize that for test? We're not gonna have to fill that in?
I'm not going to make you memorize it, but if you can't memorize that, you're going to have to be able to take the PRP, calculate it based on the depth, and figure it out based on this equation. Yeah. If you can do that, you're okay. Is Josh your husband?
Yes. What?
This is Josh.
Oh.
She said, wait, what?
Yes, that is my
Are you
husband.
okay? Curious. Well, that was a short chapter.
Let's not go on PRP.
That was so sassy.
What?
It's not intense.
I don't think it was.
That was.
How do you calculate PRP?
If it's not given.
Okay, so how do you calculate, so the question was, how do you calculate PRP? And let me run through that. So what depth are we going to be scanning at?
10 centimeters.
Okay, so 10 centimeters, okay? Our PRP equals 13, oops, that's not a 3, 13 microseconds per centimeter, okay? So if I want to calculate the PRP, then I take the PRP, oh boy, that's just terrible, equals 13 microseconds per centimeter times 10 centimeters equals 130. The centimeters cancel, and so I'm left with units of microseconds. That's how I calculate the PRP.
So you just multiply
Yeah, I multiply 13 times my depth,
13 times PRP.
and I'm good.
Take the reciprocal.
PRP.
If I want to find the PRF, I would have to take the reciprocal.
Yeah.
And so in that case, let's see if I can do this. Let's push this up out of the way. Okay, so then I would take 130, or take 1 and divide it by 130 microseconds. And I'm going to end up with something in the range of, not micro, let's see, micro 130. Let's see. 1 divided by 130 is, what, about 77 kilohertz? I don't know. At that point, I'd want a calculator. If I had to do it, I would use what we call long division and do that.
A couple slides back, it showed 76.
76 kilohertz to do.
That's what the PRF came out
Okay.
Then you have,
Yeah, 76.
Oh, 76 point what?
9.
So,
alright, that's good. Precise here.
Yeah. If I have to do a big reciprocal like this, I would just get a calculator, because I'm not smart enough to do math like that. However, if on a test I was told to answer it, I would leave it in that form right there, 1 over 130 microseconds, or you could also say that would be 1 over 130 kilohertz.
so you can leave it like that.
You could.
Less room for error.
I can't do that kind of math.
I can.
That's why I would leave it like that. I can't do that.
We could try, I mean, long division takes some time.
I went through an engineering program and we never did math like that.
You don't know how to do long division?
I know how to do long division. I'm just saying we never did math like that. If you're an engineer and you got a problem like that, you better put it into a calculator because you might make a mistake. And if you make a mistake, then the bridge falls down.
So then do you put it as a fraction? Wrong decimal can make a big difference.
No.
Yeah.
The fraction's only if you're trying to convert it to
What
PR.
was the
Okay, so then.
Mars Orbital Explorer? The one that crashed into Mars?
That's what they said
Yeah,
was
so, yeah, they missed a decimal point. Oops.
Is that the one that, when they sent 2 out to go to measure the, length of our,
I don't know. They sent it out, they had the math wrong and they crashed it.
okay.
Yeah, it was just a
They
decimal.
sent out 2 on Voyager, I think that's the one.
Yeah.
They sent out 2 first one, got stuck at Saturn, I think in the rings.
Oh, so then you would do that.
But it was, or
division.
no,
Yeah,
it
that's
stopped
what
orbiting
decimals
it,
would be
over
the
PRF, and it
yes.
just moved on.
Yeah, but I think it was more complex, but yeah, just 1 decimal for what you were just talking about. It's,
Excuse me. 13 microseconds per centimeter is still soft tissue, absolutely. Absolutely. And we're not going to change that unless, you are given like another number. So it's always going to be 13 microseconds per centimeter. We're always going to assume soft tissue. Even if you're going through the liver, which we know is a little different than soft tissue, right? We're still going to assume it's soft tissue because the average going through the liver is still going to be 1540 meters per second. All right?
So when would we divide by 2? Or when would we, just to know that it's each way, so that's why both ways, both out and back?
Okay, so the question is, when would we divide by 2? So if we have a liver, okay, and let's say for some reason somebody wrote a test and they asked a question that said, in order to image a reflector in the liver, it required a pulse repetition period of I'm going to make up a number here, 130 microseconds. Okay? How deep was that reflector?
10 centimeters.
Okay, so it would be 10 centimeters, yeah. Oop, that's not a good question for that. That would be 10 centimeters. How long did it take the sound to go from the transducer to the reflector? Then you'd have to divide by 2. Okay, so the amount of time to get to a reflector 10 centimeters deep in the body would be 130 microseconds divided by 2.
So the 13 is round trip.
13 is always round trip. 6.5 is the one-way ticket. But we don't worry about it because we're always interested in imaging, right?
So the total distance traveled is 20.
Yeah. Yeah, so as she said, the total distance traveled for this reflector that I just drew is 20 centimeters because it goes down and back, and that's going to give you 130 microseconds to image it. Absolutely.
You should make a big picture of this and laminate it on the wall.
Yeah,
I'm
it
serious.
should be like a
Right,
whole
right.
mural, just right behind, right there, so where it stands.
She said I should make a big picture of this and laminate it and put it on the wall. Okay, I will.
But with like the summer.
No, I know, with all the stuff in it, yeah. I will do that. Yeah.
Sweet. So we get to see it every day.
Yeah. And so it's just like that brain CT in the back of the classroom there. When we were learning the circle of Willis and how to do transcranial, where the vessels are on a transcranial ultrasound, I took that CT and I put it up there so that people could see exactly where the vessels are in relation to the rest of the skull. So you can always look at it and go, oh yeah, now I see why you have to have that particular angle of your transducer in order to get the basilar artery. Or the middle cerebral, I can see that it's where it's at. So that's why we put that up there. And we can do the same thing with that foundational drawing. Of course, you guys already have a copy of it from your notes. You could just like make a little a bookmarker out of it, laminate it. And then you could have it not only for your physics book, you could, every book you read. You could have it right there, and it would be available to you so that you could.
That's a little bit. But if you put it right here behind you up front, then we could just stare at it and like refer back to it when you're talking.
So instead of staring off into space, we stare out into the equation.
And not worry about it.
Don't take it down.
I do.
Yeah. We used to have a poster up here too of all the different values for segmental leg studies, so you could tell if it was diseased or not. And so it sat there for all semester, and then right before the test, they took it down, and everybody thought it would be up there. Oops. Where'd the poster go? You're supposed to know it. I can guarantee you if I laminate that and put it up behind me, it won't be there when you need it.
You just think back to this class. Just think.
Well, you should know this stuff, just, oops, that's not, that's lambda. Yeah.
It says pulse repetition period is directly related to maximum imaging depth, but did I hear you say it should say minimum?
Yeah. So if I want to image 30 centimeters deep, I have to have a minimum pulse repetition period for the sound to go 30 centimeters and come back. If it's longer, that's okay. Yeah. I could have it longer, a longer resting period. That's not going to hurt anything.
Okay, so that's incorrect in the book, because it says maximum.
Where does
It's just
it?
a different perception of like.
Let me see what it says.
Related to maximum imaging.
Yeah, that, so to the maximum imaging depth, yes. The maximum imaging depth and the minimum pulse repetition depth go together.
Okay.
Yeah. You're okay on that.
Pulse repetition.
Yeah, you have to have a certain minimum pulse repetition period in order to image a maximum depth.
Okay.
So this.
You can
PRP is 13 microseconds per second.
Yeah, we just go with that.
Okay.
Yeah, 13 microseconds per. Yeah, I'm going to answer your question. How do we separate the lines? And this is just vocabulary, so we're not going to worry about the vocabulary today. But what if our next pulse, instead of being identical to the first one, what if we like skipped a cycle? Okay, you see how it looks a little different, it sounds a little different? It comes back and the machine goes, ooh, that one's a little different.
Do you just throw it out, or is that what happens?
Well, if you're still scanning this first scan line, and you get one with this different reception to it, yeah, you throw it out. Yeah. If you're scanning the second scan line, the one that I drew like this, okay, and you got an echo back that was from the first one, you'd throw it out. You'd throw out that first echo. Okay. So that's how they actually do it.
Because the
When you're
machine's
saying
only looking.
scan line, are you talking about like horizontal?
No, I'm talking about a vertical line. So, good question. What is a scan line? It's a line of pulse echoes received from a single pulse that went from the transducer into the patient, and the echoes came back. That's a scan line.
When you say the next scan line, you're talking about a whole new line? 'Cause I'm talking about the same line.
So if I have a transducer and I send out a scan line, I send out a pulse into the patient, I get echoes back, and then I wait a bit and I send out another pulse.
So that first scan line, so the first crystal doesn't send out another scan, another pulse then?
When it
Not
receives
until-
it back.
Once the frame rate's been completed.
Yeah.
Each individual scan line has its own pulse associated with it. Okay? So when I create a pulse, that's going to make one scan line. Okay? Let's get our visual cue.
The beach ball's before.
I'm giving the beach ball a rest today. All right. So, a scan line, I'm going to make a scan line here. We're going to, okay. Well, actually, if I want to go deeper, I have to throw it deeper, right? And I have to wait longer for it to come back. If it ever makes it back. But once I've got all my echoes from this scan line, I can move over and make another scan line, okay?
So that first line, so it sends out that one pulse?
I've
and
only
it
got one
just
pulse.
waits for multiple echoes to come out, that's it?
Right.
It's just one pulse and then a bunch of echoes, and that's it?
Right, I send out a pulse, I just wait for echoes to come back, and then I can go make my next scan line. All right?
That's what's creating like our near field and our far field. I think that's what she's referring to,
Well,
like,
if I want a short scan area, then I don't go so deep, I just go shallow, okay?
With a different transducer?
Or
just
you,
with the different
you-
depth.
Oh,
Yeah,
No,
see,
it's
so
a different
depth.
PRP,
Yeah.
see how it's
Yeah.
much quicker?
Decrease.
This is my PRP.
There it went.
If I go deeper, I have to wait much longer, right?
Right. Which even though at that point, when you threw that ball, you got a reflector back from Anita, like
Right.
each
So,
person,
the idea-
that's what I think she's
Yeah.
saying,
Yeah,
is like,
that's what I'm trying to.
why
I'm
after
gonna
Anita does it keep accepting her
Right.
pulse and
Yeah,
her pulse
yeah.
and her pulse?
Why is it,
Right.
because if it gets that echo back from
That's
Anita,
pretty
why
good.
is it,
That's what
why
creates
is
our
it
make
not
the
in
picture.
far
So
field?
the minimum time, is what it takes to go that distance.
Right.
But what if I just wait a while for all the echoes to come back, and then I come over and make another scan line? And then just wait a while.
You won't get a picture.
I'll get a picture, but it'll take longer.
Would it be more blurry? No.
It just takes longer.
Is it kind of like if you sent out a bag of little balls, and then you sent out one bag of little balls, but then you're waiting for each little ball to come back to you?
Right.
Some of them reflect off, some of them bounce off one person.
Right.
Oh.
Yeah, that's what it's kind of like. So I send a bunch out, I gotta wait for all of the echoes to come back. Well, the truth is, I send out one ball, and everybody rips it into little pieces, and the little pieces come back. We don't wanna do that experiment.
Okay, so if you, image depth is at Marcus,
Right.
okay.
So
So
my,
by the time you get Marcus's echo back, you'll
I
already
have-
have Eric's structure, you know, and so on. So you already have, you
yes,
get an echo from these, but you're just waiting for the time for that last one to come back,
Yes.
and then it just moves on.
right,
So then it's just anything after Marcus, it throws out, that's why there's no
Yes.
interference.
right,
Okay, that makes sense.
yes,
Okay.
I have a question.
yes.
Does that have to do with echogenicity also? The way
So-
things appear?
So the question is, does that have to do with echogenicity? No. Echogenicity is how much force the ball comes back to me. Okay? So if I toss it to you, okay, that's gonna be a bright echo, right? That's gonna be a little weaker echo, right? And then that's a little weaker. And because we're going deeper, right, sometimes it's attenuated and it never gets back, right? And we'll talk about how that works on another day. That's called amplification and compensation. Okay, so yes, the echoes close to the transducer can come back with a lot more force. And we plot the brightness of the echo based on how much energy the echo has. So yeah, the near ones can have a lot more energy. The far ones are weaker, so we compensate for them, right? And we call that time gain compensation. That's these little buttons.
Yeah.
Yeah,
Oh.
TGCs, or DGCs, yes, depth gain compensation. So those weaker echoes coming from deeper, we compensate by giving them amplification. Yes.
So is that why whenever we're scanning, you'll come up behind and you'll put them at like a diagonal?
Yes.
So that those
I-
ones are.
So when you're scanning and I come up behind you and I make adjustments to your TGCs, what I'm doing is I'm trying to make the image look the same at the top as the bottom. I want the same brightness level in that liver all the way through it, because the liver is the same tissue. I want it to represent as the same tissue. So I almost always turn up the top because the machines automatically decrease that. And then a lot of times turn up the bottom too to make a nice smooth image. All right, have a good day. I hope that was useful.
Yeah.